This is topic 3.2, threshold of sediment motion and its transport. The initiation of motion of sediment particles on the bed is analyzed empirically rather than by theoretical equation of motion, like equation 7 given earlier in topic 3.1. It is related to an empirical parameter or a function. The entrainment function is defined by the flow shear stress tau 0 divided by the density difference and by GD. Since this entrainment function was proposed by Shields, it is also called the Shields parameter. The physical meaning of this parameter can be found by multiplying the numerator and the denominator by the area AS of contact of the particle with the bed. Then the numerator represents the horizontal force acting on the top surface of the particle, and the denominator means the weight of the particle. The weight of the particle multiplied by the friction factor is the resisting force against the horizontal motion. The value of the parameter then is large when the force tending to move the particle is large compared with the resisting force, and vice versa. The value of the Shields parameter at which the particle starts to move is called the critical Shields parameter, theta CR. The value of the corresponding tau 0 is called the critical shear stress, tau CR, of the particle of diameter d. The critical Shields parameter may be different from one particle to another and in one flow condition to another, but an average value for most sediment particles may be determined. Shields found that it is a function of the non-dimensional diameter d star, same parameter used for the fall velocity. It is seen that theta CR decreases from a value larger than 1 to about 0.03 at d star equals about 30. It is about constant of 0.05 for d star larger than about 50. For large values of d star larger than 50, the value of critical Shields parameter is about 0.05, but it has been found that the local shear stress may vary depending on the shape of the bed surface. So therefore, when theta s, the Shields parameter theta s is smaller than the critical Shields parameter theta CR, there is no motion. If it is between theta CR and 0.08, there will be transport that occurs if there is a bed form like ripples, which will be explained later. If theta s is even larger than 0.08, transport will occur even on flat bed. In addition to the Shields criteria described above for initiation of motion, the particles may be suspended and moved with the water if the fall velocity is very small, and a suspended mode of transport will occur. Now, if the shear stress is larger than the critical stress, the sediment particles will move on the bed. The amount of the volume of the particles crossing through a cross-section per unit width across a flow near the bed is the bed load transport, QB. It can be written as the velocity of the sediment particles multiplied by the thickness of the layer of moving particles, delta S, and the concentration of the sediment particles, CS. It has the dimension of volume per unit width per unit time. The transport normalized by the non-dimensional quantity with the same dimension like this is called the transport factor, phi. The transport, therefore, are usually given for the bed load factor phi in terms of the Shield parameter theta s and the critical Shields parameter theta CR. There are various transport formulas that have been developed over many years. The early one is proposed by Einstein, who is a nephew of the famous Albert Einstein, proposed in 1942, is an exponential form. The next one, proposed by Meyer Peter Müller in 1948, which is still used by many researchers, is written in this way. Ashida and Michiue, proposed in 1980, is given by this form. Nielsen in a similar form. And now we have a different form proposed by Van Ryn. The detail is not given here, but there are a number of formulas, and they are used depending on various conditions, such as these conditions. And that is the end of topic 3.2.